Alright, so here's a sea spray aerosol particle. If we zoom in at the surface, as you all know, there's a bunch of different chemicals that could be there, but one of the most abundant ones is palmitic acid, which has 16 carbons. What's kind of interesting about palmitic acid is actually found in coconuts, and it kind of helps it float on the surface of the ocean. But I'm getting ahead of myself. Let me back up a little bit here. Okay, so palmitic acid. Let's say we want to understand how it behaves at the surface. We should simulate it. We should watch how it moves through time like we're doing here. How do we do that? Well, that's what I do. I use molecular dynamics simulations to study how sea spray aerosols molecules move through time. So let's zoom into palmitic acid here. Okay, so palmitic acid has a lot of carbons in brown, hydrogens in black, and oxygen, 2 oxygens in red. If we zoom into a bond between 2 carbons and we simulate it with MD, we'll see it also move about that bond. The bond will get smaller and bigger through time. And what that is called a harmonic bond. And so what this is showing here is the harmonic bond going through time. And we can model that using basically Hooke's law. We can also model an angle and how an angle changes through time. So let's imagine we're simulating this angle here and it's changing through time. We can also model that with Hooke's law using a harmonic spring to describe the change in the angle with an equilibrium angle, say this one. Okay, so we have harmonic bonds, harmonic angles. The first motion I showed you was dihedral angles, and these are just some of many components that make up the force fields that people like me, computational biophysicists, use to study the motions of molecules through time.